And I will be talking today about how we used Mathematica quite essentially in proving a long-standing conjecture in spectral geometry. So first of all, let me introduce the problem. What is this conjecture due to Pólya? And it's conjecture in a subject called spectral geometry, which is related to behavior of some solutions of partial differential equations. I'll try to avoid the technicalities here, but I do need to introduce some notation. So we consider omega, some given bounded domain in a Euclidean space of dimension greater than 2. And in this domain, we consider spectral problems for the Laplace operator, the sum of second derivatives with respect to coordinates. Namely, we're looking for functions u defined inside the domain, which satisfy the differential equation minus Laplacian u equals lambda u, when lambda for the moment is an unknown spectral parameter, and which also satisfies some boundary conditions on the boundary of omega. Either we assume that u is 0 everywhere on the boundary, and that's called the Dirichlet condition, or we assume that the derivative of u with respect to the external normal to the boundary is equal to 0 everywhere on the boundary, and this called the Neumann condition. And in either case, we're looking for the values of parameter lambda such that there exists an untrivial solution of the problem. And these numbers lambda, such that such solution exists, are called correspondingly Dirichlet and Neumann eigenvalues of omega. And it's well known that there is an infinite sequence in each case of such eigenvalues, which we enumerate. They may be with a count of multiplicities in increasing order. All the Dirichlet eigenvalues are positive, and the first Neumann eigenvalue is 0. And eventually the sequence of eigenvalues converges to infinity in such case. What is the problem with this spectrum? Problem, why it's interesting and difficult. On a physical level, the eigenvalues lambda describe the frequencies of fundamental tones and overtones of a membrane or drum head having the shape of omega, and hence the relation between the shape and the sound is important here. And the famous question of Mark Katz, can one hear the shape of a drum, means whether one can determine the shape from knowing all the eigenvalues. But the problem can be solved analytically only in very, very simple cases, for example, for boxes. And numerically, using finite element method, one can find some number of eigenvalues reliably, say 200, 300 for a given planar domain, for example. But can't say anything numerically about higher eigenvalues. It's a hard problem. So there are some famous questions and problems concerning these relations. And usually, instead of looking at individual eigenvalues, one looks at the so-called counting functions of eigenvalues. Namely, we count the number of eigenvalues below a given value of lambda squared. Lambda here is a positive parameter, and call it the counting function, either Dirichlet counting function or the Neumann counting function. I'll show an example below in a second, but it is known that these counting functions grow proportionally to lambda to the power dimension times some universal constant depending on dimension times the volume of your domain. And this relation 1 is known as Weil's law, and it's more than 100 years old. And our story begins about 70 years ago when a famous American-Hungarian mathematician George Pólya conjectured that for any domains omega and all values of parameter lambda, you have inequalities between Dirichlet and Neumann counting function and the leading term in the asymptotics too. The Dirichlet counting function always lies below the asymptotic value, and the Neumann counting function always lies above. And it's important that it should hold for all values of parameter lambda, not just large ones. So this is a picture of two counting functions, Neumann in red and Dirichlet one in blue for a three-dimensional unit ball in this image. And the black curve represents, in this case, constant times lambda to the power of 3 curve. And you can see that at least for sufficiently small lambda, it is indeed lies between two counting functions. So Pólya proved almost immediately after the stating this hypothesis that it is true for Thailand domains omega, namely such domains that the whole space can be filled with non-intersecting copies of the domain. So any triangle is a Thailand domain or a box. And that basically was all the progress done in the last 70 years. In particular, the conjecture remained open even for the disk, because obviously disks don't tile the plane. You can't cover the plane by a copy of a single disk. And this was until about last year, where together with my courses, Nikolai Filonov, Iosif Poltorovich, and David Sher, we proved this conjecture not only for the planar disk, but also for high-dimensional balls and some other shapes, for example, for sectors and annuli on the plane. This was published in several papers, and some papers are still in preparation. So what is the trick and how do we use Mathematica here? And to start with, we need to talk about Bessel functions, standard special functions you might have encountered. And this is because in case of a disk, the eigenvalues of Dirichlet and Neumann Laplacians can be explicitly computed. The Dirichlet eigenvalues are the squares of roots of Bessel functions, and Neumann eigenvalues are the squares of roots of derivatives of Bessel functions. Unfortunately, there are two indices here, the index of the Bessel function and the index of the zero. And rearranging these two index, double index sequences in one increasing sequence and therefore count how many of them are below a particular number, it's impossible. And even if you try to do some numerics, computing, for example, 50,000 zero of Bessel function of order 100,000 is not a trivial task. For example, Mathematica doesn't cope with it in 10 seconds and probably not even in much longer time. And to fight this, we introduce, instead of Bessel functions, the so-called Bessel phase functions, which are defined here, and they relate to kinds of Bessel functions of the first order, Bessel J function, and Bessel function of the second order, the Bessel Y function. And it's a separate question how we can compute these functions. We can, but it's not needed, because what we do, instead of computing them, we derive new and very efficient two-sided bounds for them in terms of some elementary functions. And elementary functions are trigonometric functions, inverse trigonometric functions, polynomial, and roots. And then this is where Mathematica came very handy, because at some stage we needed, in proving these bounds, do incredibly complicated, straightforward but very complicated calculations. For example, change variables in some parameter-dependent polynomials of very high degree. I'm not sure we would have managed to do it by hand. And then the trick is that the zeros are actually can be expressed as inverse functions of the phases at half integers factors of pi. Here m is an integer. And as a result, bounds for phases give almost elementary bounds for zeros in terms almost here, because we do need some inverse functions here. So without formulating what the exact bounds are, here is a pictorial example for Bessel function of order 5. The blue curve here is the actual phase. The green and the orange curve are lower and upper bounds for the phase, and it just shows the bounds for the zeros, not just Bessel zeros, but some other zeros of Bessel functions of the second kind, their linear combinations, and so on. As the further you go, the bounds become even better. And just to illustrate the accuracy of our bounds, here is the contour plot of the logarithm of the maximal relative error of our bounds, depending on the index and the number of zero. And for example, for Bessel function of order 10 to the power of 4 and to 0 of order 10 to the power of 6, we obtain the bounds with maximal relative error of 10 to the power minus 14. So bounds work very well and beat, by the way, all the existing bounds. So where do we go from there? And here is the essential part of using Mathematica. Once we use the bounds, we reduce the proof of Polya's conjecture in our cases to the following problem in number theory. We need to count, with probably some weights, the number of lattice points, points with integer coordinates, under the graph of a monotone function. And for the disks, so we count under a graph of very particular functions, the g of lambda, given by this explicit expression. So here is the picture, and we need, I draw some lattice points and two functions, g of lambda plus 1/4 and g of lambda plus 3/4, so shifted up by a different amount. And what we need to show that the lattice point count in one case is less than the twice integral of function, which is fortunately easy to compute, lambda squared over 4, and less and at the same time, the number of blue and orange points together exceeds lambda square over 4. And in general, we prove it analytically. But in the case of the upper bound, our proofs leave a gap of lambdas where we couldn't prove it. And we close this gap by using a computer-assisted algorithm. But it is a rigorous computer-assisted algorithm in a sense that we need to satisfy two important conditions: a finite number of steps, and all calculations should be exact without any floating point approximation. And if you look at the function, of course, you can't generically evaluate it analytically. So to do this, we use what we call verified rational approximations of square roots, inverse trigonometric functions, and so on, which is in essence a one-sided rigorous version of Mathematic's rationalize command with rigorous proof on each step that the inequalities we obtain are indeed valid. And the proofs are done automatically, again, using it's an algorithmic approach to that. So here we have a computer-assisted algorithm. And in some cases, for high dimensionables and for annuli, the functions are much more complicated, the weights are much more complicated, and the computer-assisted algorithm is much more complicated than for a disk, may take quite a long computational time to complete, but it does complete, it provides rigorous proof of the conjecture. So just to summarize, basically we proved the 70-year-old conjecture using tricks from ordinary differential equations, special functions, number theory, and an essential part are some computer-assisted algorithm using both mathematical, numerical, and analytic capabilities. They are primarily analytic here, but also some numerical. And just to say that I've used Mathematica in a variety of other problems, mostly from my field, spectral geometry, but also related questions in Riemannian geometry, poor and applied PDEs, for example, linear elasticity, waveguide analysis and south propagation waveguides. This is mostly analytically, but also in finite elements analysis, and also in some programmable typesetting. If you want to see examples of some of the scripts are on my web page or at this address, and there are some other scripts in other situations. So thank you very much for your attention, and if you have any questions, welcome. Thanks a lot. Okay, there are various questions. I will be reading them out. Is the talk notebook available? I can't see a link to it. I haven't uploaded it, but if you email it, I will happily send it to you. Question for Pólya. But another question in general from Matt. In general, is it possible in Wolfram language to input a set of axioms and apply them to improve in order to detect mistakes and contradiction? Not as far as I know in Mathematica, and it's a big problem, computer-assisted proof, computer-verified proof. People are working on it, and but it is hard and difficult. Another question from Matt: wasn't Pólya's conjecture disproved? Pólya had a lot of conjectures, and I'm talking about Pólya's conjecture in spectral geometry. There is another Pólya's conjecture in number theory, and it has been disproved, but Pólya's work was a great mathematician, so there were many conjectures. interesting to see the code for calculations themselves. The full code, reasonably documented, will be available, is available on my web page, and I will be posting further codes, for example, for high-dimensional balls and for annuli, which are much more complicated later on. Some of the code was simplified for the web, but there is full versions available at request at any time. Yeah, someone might feel corrected that Polya's conjecture number theory is false. This is unrelated except for the name of the person who corrected it. Okay, thank you very much. Yeah, any further questions or queries? Okay, there is a question in chat and also whether the proof was computationally intensive or computer time intensive. Depending on the version, computer time in the latest, hardest version was probably about half an hour. Computationally, it's a lot of computations, yes. Thank you very much again, but if there are any further questions, I'll just show that my email and web page on the first page of the talk, and I'll ask if you have any further questions, I will be happy to answer them personally by email. Okay, thank you very much again, and I'll stop video and stop sharing now, but feel free to ask further. Bye.